basically, this is from application programming, but classes are a key aspect of what you are doing. So basically what we're looking at with classes, so Python is a language that basically leaves all the types over to runtime, but that doesn't mean that there are no types, and you need to take that into account. But object orientation is a way of thinking about structuring your program. And the idea is that you combine your data with the code that acts upon that data, and kind of, so should have this slide first. So that is what kind of object orientation is about, and it combines a number of different elements in this concept. So it is, a programming paradigm, but it also combines a number of things that you want to do in your programs. And at the same time, you may really need to realize that it does not do everything. Free functions, as you have been using up to now in Python, can be the right solution for what you want it to have. So it is not a silver bullet, so to speak, or a panacea, not a cure of all ills. If we had one of those at this moment. And it works well with certain kind of problems, and you may have seen that so when you look at Flask, it has objects. But object orientation is more than just using a dot notation to access a method that relates to that particular data. It is that, but it is also about organizing your data. So what makes up this this object orientation? So one of it is just the ability to structure your data, to have data that is related, so that belongs together, is structured together, and kind of is hidden away within your program, within a bit that, okay, only the code within this class will actually access this data directly. Everything else needs to go through this interface that can police this, can manage that. So that also leads to things like modularization, where you want to not put everything in one big file, and then it becomes a big mess and you don't know what to do with it. No, it can also use your code in a more flexible way, so to speak. There's code visibility. In Python, this is less important than with other languages, but you have the conventions where you use properties like with an underscore in there, so that it is clear to users that they shouldn't directly access this. And you have the property decorator to help you with that. Classes also really allow for code reuse. Of course, the easiest way of code reuse is just calling a method. The method is the code that you're going to reuse there. And an interesting aspect, and that is a key programming thing, is the idea of abstraction. To try to hide away complexity into a smaller part. You can do that with functions, but if you have data, you do that with objects or with abstract data types. So a data structure is basically just something where you group data together. It's fairly simple, and it is where you want to look at, okay, how does this data work together? How is this structured? An example of such a thing would be, and this is in Kotlin, a data class which has, so Kotlin is a typed language for the JVM, so it's an alternative to Java, so to speak. But such a data class, what it does, it basically holds all these values or variables, house, street, postcode, town, as strings. So you have to define the type when you define members of a class in Kotlin. You can also do that in another language such as C++. Let's skip this a little bit because this goes a little bit about what it looks like. For Python, that is a little bit over the top, not relevant at this point. We're basically looking at a structure of data that is combined with elements. And yeah, skip that bit about references as well. I'll create a cut down version of the slide set for you that doesn't include all this after the fact. And this modularization is the idea of having things that group certain responsibilities close together and other parts not. So basically, if your particular code is not doing something, you do not want to actually expose it at that point either. And that is what modularization is about. So modularization in this case says, okay, I put this functionality in this class, and this class is the and everything else it uses that needs that access just uses this class and doesn't need to worry about how it's implemented. Of course, you also have files to group things and folders and stuff like that. And that's where Kotlin module or Python modules come in as well. So then is this abstraction stuff. So what is abstraction? Basically, abstraction is trying to kind of understand something by kind of having a more abstract, a model of it. You kind of look at it for what it is in a, if you kind of take away all the detail. And in programming, that means that we are going to basically have something that we say, okay, this is the way you can use it. This is the interface. This is what I give you to do. But we don't tell you necessarily how it is implemented. Now, if something is not particularly well documented, or if there's an error, it is very good to still have access to the source code. And it's often there for that particular purpose. But for normal day-to-day programming purposes, you don't need that. You don't need to look at how is this particular concept implemented. In Python, often the implementation is actually in binary code and not in Python, so then you cannot go and look at how it is actually implemented underwater. And how do we translate this then into our actual program? So one of the ways you do that is using for some abstract data type. So basically, this is what the Java interface is. But for Python, you don't have the separation between classes and interfaces, but you can still use this idea. And Python also uses something called duck typing. Duck typing is the idea that if it looks like a duck, it sounds like a duck, and it quacks like a duck, it is a duck. Basically, you just call the method that is supposed to be there, and if it is there, it will work. And if it's not there, it will not work. That makes for very easy coding, but it also means that you have less help from the compiler in finding your errors. But what you do is you basically say, okay, we only specify what can happen, what can you do with this data, rather than how does it work underwater. We don't really want to know about that in many cases. There are cases when you do need to know, because there might be speed implications for how it works, or memory implications, or other kind of implications that things. Or in the worst case, and please don't do this too much, is when you have code that you want to say, okay, I'm going to actually change this code, to say I need this system to do something that it's not supposed to do, and I'm going to look into the guts and see how I can actually kind of go around the intentional design and work with it. And then you need to look at the source code and how it actually works, and then hack around stuff. You sometimes can do that, and sometimes that's the only way in which you can do stuff. But it is also an approach that is very easy to break stuff. You don't necessarily want to do that. So one of the things you can do with this is very much that you don't want your user code to depend on the particular implementation, even if you write both yourself. Why? Basically, the problem if you depend on a particular implementation is that you are then going to be stuck to that particular implementation. You cannot change your mind, so to speak, for deciding I wanted to actually do this in a different way. You're then stuck with it. We don't necessarily want that. But that's what you get with if you put everything together. So if you have a larger program, you want to basically have different parts of the program only have a cursory understanding of what the other program does or how it works. You don't want to need to go into the details of another part just to be safely changing something. Because one of the things that you may not realize, but is a very important thing to in programming, is that programs in reality actually are much more often modified, updated, maintained than that they are written from scratch. I would say the vast majority of times when you start working in an actual job, especially if it's the actual job rather than a placement, you will be working with code that someone else has started. You will work with your entire team. So the idea is that you want to be able to think. So one of the aspects we're also talking is like when we're talking about there are aspects that need to be true for all implementations. This is called, by the way, the class invariant, something that never changes. This is often only visible through your documentation. So that is where if you want to implement an interface or a class, you do need to read the documentation. Reading documentation is a key coding skill. You can't just say, oh, I'm trying how this works. You can a little bit, but it breaks very quickly, as you saw when I did the Flask bit. So, and it's also nice, if you have these abstractions, you have these interfaces that you can document. Basically what you can say is, okay, if it works on the interface, it should work on all implementations. In Java, you see it with the list types, etc. So, and we can even have multiple implementations that have multiple different strengths. Or if we're talking about databases, we have different database interfaces that are database interaction classes that work for different database types. In that case, it's obviously impossible to have the same code for the different databases. So we want to just have the same interface so that you can just strip out, okay, I have MySQL, I've got Postgres, I've got SQLite, etc. As long as your program only sticks within the subset of common SQL that is supported by all those databases, the rest should just work. Then when we have object orientation, we have this code reuse stuff. So what you want to really do all the time is reuse code. Make functions to wrap your code. Make classes to wrap common state and common behavior. Use inheritance if your classes if there's kind of common parent behavior beyond the individual behavior of the child classes. And object orientation provides some ways of doing this. But there's other ways, such as we can just use functions. Yes, the very always popular among students approach of copy-paste reuse. Copy-paste reuse is just asking for trouble because there are so many ways in which your code can break and you don't necessarily want to support all of that. But that's where copy-paste comes in. So normally if you're copy-paste editing something, then, and you're not editing it crazy like I just did with the method that I wanted to do for users. Of course, that's also example code. Then you would have common code. So, for example, when we looked at the documentation for Flask, we saw that they had like these error methods for handling there's no file. What you're doing there is basically saying, okay, we're going to not have every function do its own error message for file resource not found, but it's doing it in a generic way. You have a consistent look and feel of your website, and if you want to change that look and feel or anything like that, it all works. You only need to change it once, and everything else that uses it, you don't even need to think about it. It automatically gets the new behavior. So templates. So code templates is something that is not in Java or in Python. In a way, the templates that Flask has are templates, but they're kind of different templates. They are output templates rather than code templates. Doesn't matter. The idea is sort of the same. You kind of have variation where you can then plug in different behaviors depending on the parameters you give. And it's also in a way that those decorators in Python work. Those decorators take some Python code and then do something with it, and then you get a new function as a result of that. Generics in Python, you do not need that because you don't need to use type. So, but generics are basically the idea of saying, okay, I want to have these containers that work with whatever you put into it. In Python, that always works because the types of variables are weak. Everything is basically whatever you put into it. Fully dynamic typing. Lambdas we didn't cover, and then we have things like inheritance. So what does inheritance do? So inheritance is basically when you have types, when you have things that you want to express that basically are variants of the same thing. So like if you have a UI, you have a concept of a particular widget or a view that you're displaying. And there's different kinds of widgets. There's text input widgets, there's buttons, there's labels, there's scroll panes, there's groups, there's radio buttons, many different kinds. But there's a lot of stuff that they have in common. For example, they all have a size, they have a location, they have a way of drawing themselves. That code can be shared by all of them. So what you do is you say, okay, they're all a particular view, then they are just a child or a descendant of that view. And in such a case, we can use inheritance. But remember, inheritance is a public relationship, also in Python. It is something that is visible. You can't just say, oh, I only need this behavior, but I don't want to be seen as if I am that. If you want to just take some of the behavior, some of the code of another class, but without promising to fulfill the contract that you need to fulfill as if you as if you are that particular class, because that's what inheritance is. Inheritance is a relationship where you are required to meet the contract of the parent. Everything that's true for the parent must be true for a child. So, a common example is, for example, what if we have rectangles and squares? Can we use inheritance for rectangles or squares? So, is a rectangle a particular square? In some ways you say, yes, a rectangle is a square. Math tells us it's a square. But if we use in programming concepts, that isn't exactly true. Why? In programming concept, when we have a rectangle, if we have a proper rectangle, we might be able to change the dimensions, the width and the height. A square might also be able to change the dimensions, but of course its width and the height are the same, otherwise it wouldn't be a square. And so if we have a rectangle that happens to have equal width and height, it is conceptually a square, but not in terms of actual class. So we can't say, okay, a square is a rectangle, because a rectangle requires you to change one dimension and then not automatically change the other one. That's unexpected behavior for a rectangle. If we have a square, then so a rectangle obviously is not a square either, because a square we expect that the width and the height are always the same. So that is the challenge of the relationship. You must meet the contract of the parent, and sometimes things are not objects. And if you can't think about, okay, what is this object, or if you just say this is actually behavior, it isn't actually an object, or you can have an object that just wraps functionality, like the functor object, a function object. Basically, the only existence of it is that you can call something on it. In Java, you often end up creating those things, and in Kotlin or in Python, you do not need to. So inheritance is basically the idea that you reuse some of the implementation of a parent and the state, but that you in turn also promise to fulfill its contract. That's also where the strength of inheritance is that you can have different children and you don't need to know any of their details if you want to treat it like a parent instance. So a view framework, a UI framework, just says, okay, these are views. I just need to draw them. Oh, there is a mouse click pressed here. What do I need to do? I don't know. View, there's a mouse click. And then the particular view says, okay, I'm a button. I'm going to use this mouse click to do a button press. Oh, I'm a label. I'm ignoring this mouse click. Oh, I am an edit text. I use this mouse click to position the cursor in the edit thing and to get the focus to this particular control. So that way you can also very easily write your own controls, because the framework doesn't need to know about your control then, because your control is also a valid parent view or control that it knows about. But this is where inheritance and polymorphism comes in. The polymorphism is basically the idea that when you call a function, the actual function implementation you get that is called is determined by the type of the value that you're actually doing it on, not the type of the variable. In Python, obviously, variables don't have type; only values have types. But polymorphism is using that to determine the function to call. And in Python, if you have a free function and you pass it an object, again, that free function is determined not by the value, but by the context of calling it, which function is being called. And finally, is code visibility, is the idea of actually hiding parts of your code. Let me have a quick look. And the idea is that makes your things easier to use. So yes, so there are some class principles that are very useful for you to know. And again, this concept is true whether it is Python or JavaScript or Java or Kotlin. So there is the class invariant. I already mentioned that. The class invariant is about making sure that there are things that just need to always be true for the entire class. Give me a minute. My battery is almost running out. These are really crappy rechargeable batteries. I should be back. Sorry about that. So the class invariant is basically the idea that certain things need to be true always for an object, for the class contract basically. And some of that is can be enforced in code, but a lot of that is also enforced in your documentation through users of your class, or especially inheritors of the class, reading the documentation and making sure it stays true. If you don't do that, you get really confusing behavior. So be aware of that. It needs to be clear. And one of the things that you might also say is there are sometimes classes have state. State can make something a little bit trickier, particularly if you not say, okay, this is a property that is just, I'm holding this property. But if you have state, like a network connection, that means that certain things cannot be called at certain times, which is a bit tricky, and you want to avoid that if you can, but you can't always avoid that. But what it does mean as a class invariant is that you normally want to make sure your objects are in a valid state as soon as the constructor is finished. And valid means that the class invariant is true. So the class invariant can be saying, okay, there are two states, there's an open file or a closed file, and when you start it will always have an open file. Or have a file that needs to be opened, so there's kind of starting a file, an open file, and a closed file that is now finished. Might be three states, and those three states have these properties and they should remain true, and you use your methods to make sure that is true. And that's why you also don't want other code to go in and look at your internal guts, so to speak, the internal functions or the internal properties, because then you cannot make this true. But the key part is that your constructor needs to make sure that everything is initialized and set correctly, so that invariant is true at that point in time. When we have inheritance, this is a relationship. Again, I already said so, but a child must follow the rules of the parent. You must always be able to treat a child like it is a parent. And yes, it's a public relationship. The other approach is something called composition. So that is basically the idea where you actually say, I has a relationship. So I have a property that holds this particular class. And you might just delegate functionality to that class to let it do its thing, but you then have full control and you cannot be treated as if you were an instance of that helper object, so to speak. So it gives you a lot more freedom to do that. Like I said, when you inherit a class or implement an interface, you promise to meet the contract. You can reuse shared code. You can also call parent code in a child code. Sometimes that's necessary. It's not always easy in a language to specify that is required. But documentation is really important there. Talks about polymorphism. Basically the idea that when you have an object of a particular type, that object determines what the actual implementation that is being called when you call a particular method. In duck typing, as Python uses, that is always true, because you just have an object and it has methods and you call that. It is not always true in other languages. In Java, it is basically true. In Kotlin, it is also basically true. But in a language like C++, you can actually also have functions that do not follow this rule. So you basically need to enable it for your specific functions. We will not go into that, how to make that work. So one of the tricks there is also to help with correctness. Things like Kotlin has an override keyword, because sometimes you need to make sure that when you override a functionality that the methods are actually compatible. So in Python you can't have multiple functions with the same name, so that's easier.